So I'm going to skip rigid frame. We talked about that yesterday. But I want to show you a little bit about the frame behavior. This is quite important to understand how the beam and column sizes or relative dimensions, they affect the behavior. And this is something which is quite important in the design of tall buildings, in the sense that while we are looking at the tall buildings, the thickness of the beam, or the depth of the beam and size of the column, relatively, they are very important. Okay. And so there are three examples here. One is that the beam and column are of a normal, regular size, as sized for a normal building, not for a tall building. So the column is not that big, the beam is just enough. In the second example, the beam is very deep, much bigger than the column. And the third example, the column is much bigger than the beam. That means in this case, it's like a flat slab. And in this case, it's like a very heavy floor, and here it's a normal one. So when you change these dimensions of the beam and column, the behavior of the frame is affected by that. So you can see from here that the deflection is now different, and pattern is different for each one of these frames. If you can see a little bit more, if you watch closely, here the beam and column, they are both deforming. So you have deformation of the beams and columns both. So when you sway the frame, the column also bend and the beam also bend, because the stiffness is nearly similar. In this case, the beam more or less stays straight. They do not deform too much laterally, and columns are the main that deform. So which means that the columns in this case are weaker than the beam. In this case, the columns are much stronger. They are not bending, but the beams are now bending a lot, or the slab is bending a lot. So the deformation pattern and displacements will be also different. Now you can see that these three cases for the same loading, this one seems to have slightly less deflection, more deflection, and slightly the medium. So lateral displacements can be controlled either by beam size increase or column size increase. But this is something that we normally do not want in a building. We do not want weak columns and strong beams, because if a failure occurs in a column, then the whole building can collapse. What we really want is a behavior of this kind, where the columns are stronger than the beams, so that the failure initiate in the beams, and we can also use the deformation of the beams basically to dissipate energy and form hinges and many things, non-linearity and all of that stuff. So typically, we are looking for this behavior. For tall buildings, this is almost automatic. Why? Because when you have very tall building, what happens? What happens in a tall building? Columns are big because the gravity load keep on increasing as you go up. So the span may be the same 6 meter or let's say 8 meter. If one story, then the beam will be about 0.7 meter or 0.8 meter deep. Column may be only 30 by 30. But if the same building 8 meter is 40 stories, column will be maybe 1.2 meter. Beam will still be the same, 0.8 or 0.7. So column will become bigger automatically. So for tall buildings, generally this model automatically becomes true. And if you're using flat slab, then this is normally the case. But the problem is lateral deflection. Sway is too high in that case, because each column starts to act like a cantilever, kind of, because the beams do not provide any much stiffness comparatively. So the sway is very large. That's why for tall buildings, frame alone does not work very well above a certain level, right? For short buildings, this is the case, or this is the case, then it can work. But this is not something that we want. Now, if you look at the bending moment, yesterday we saw that the bending moment patterns, and somebody draw for one frame, and this is now drawn for many frames. You can see here that the bending moment in the beam, lateral bending moment in the beam keeps increasing every floor. So each floor, the bending moment for the beam is increasing. So every floor beams will have different bending moment because the lateral load is being added up, is accumulating, right? Same is the case with columns. So the column bending moment also is increasing as we go down and becomes nearly zero at the top. So it's not constant. The bending moment and shear forces in the column increase from the top to the bottom, even though the gravity load also change. Here in this case, you can also see that the beams have similarly large bending moments, and columns have smaller. And here you can see that column has larger bending moments. At the same time, there is no reversal. Here if you see, bending moment in the column is positive and negative, right? Top and bottom. I mean, the direction is both positive, reverse moment like that. But here is not the case. Both moments here and here are the same direction, which means that the column is not really bending between two floors. The beams are too small to make the column act between the floors. So column effective height actually may be much longer, because of the fact that the beams are unable to twist the column completely. So this moment is still red. Here the moment is two colors, yellow and red. So that means the moment is actually completely reversing from top to the bottom because of the beam. This is a fact that many people may not realize, that the columns do not act as one floor to one floor. The column may be acting between several floors because the moment is not being reversed each floor. So depending upon the size, the column behavior, and that is the reason why this has larger deflections than others. Okay? So relative size of column and beam is very important, and because we are mostly in this state, this is not a good model. We need something else. We need shear walls now when you go tall building, because frame alone with very large column and small beams will not be very strong or will not be very effective, or especially flat slab. So we talked about the frame and shear wall, putting them together yesterday and on Wednesday, and we talked about how the deformation of the two is opposite, so they start interacting and they start contributing to each other. So I put here, this is very interesting, please watch this slides carefully. The effect of the column and frame interaction, and it is all controlled by the beam. So in this case, I put a shear wall here, and I put a normal beam, a smaller beam actually, that connects to the shear wall and the next column. Here I put the same beam, because this is a smaller span, so I put the beam small because that's what the gravity load will require. This one I use the same beam as for the long span and go directly here. Here I increase this beam size to be larger than this one. Now this is very interesting, because if you design for gravity loads alone, you will end up with this situation, because short span, smaller beam. If you use this beam for practical purposes, because easy to construct, you can still do that. This is something that nobody will do, because they will think that I have a short span, why do you need a bigger beam, right? But the effect of, or the interaction between the frame and the shear wall is actually controlled by the connecting beams. And this is what determines how much interaction will be present between the two, right? So let's see how they behave. So here you can see that when this wall is bending, it is almost bending like a cantilever, and frame is bending, and these beams are bending in between. So there's a large deflection here and not much interaction between the two. So in fact, this frame and this wall, they are side by side, they are going together. Of course, the deformation pattern is slightly, so this change is slightly because of the wall, but this is called first level of interaction, in which there is no force transfer between the wall and the frame. They are just connected together, they bend together, and they interact a little bit. So there is some tension compression between them, but they did not really act together like we wanted them to act. Second case, when the beam is slightly bigger, you can see that the pattern of the wall bending is not changing. Here it is just bending almost like cantilever. Here now the pattern is slightly changing. And when I increase the size of this one, now you can see the deflection has reduced a lot, and at the same time the pattern of the frame deformation is now changed a lot. So which means this connection between this wall and beam is very critical to utilize the frame shear wall interaction. These are normally called link beams or coupling beams or coupling between wall and frame or coupling between wall and wall. And this is a very interesting problem. So what happens is that if you, let's say, you put a beam like this, you will find that this beam has a lot of bending moment and a lot of shear. And you will increase the size to design for that. And when you increase the size, the bending moment and shear will increase more because the stiffness has increased. So you will increase more and it will keep attracting more forces. So sometimes even a whole floor of beam may not be enough to design that. That's where we have to stop increasing the size and use some alternate mechanism to design these link beams, and I will talk about that. So you can see from here the shear force here, shear force here, here, and also look at the value of shear force changing from top to bottom and here. So the shear force between on this small beam is very large in this case. So, no, I'm sorry, this is bending moment. The bending moment between these, not for shear force, this is bending moment. This is the bending moment for this beam here, and here the bending moment is quite large. So there is a large bending moment in that link beam, which is helping to couple the frame with the wall. And if this beam does not have enough capacity for the bending moment, you may want to increase it. When you increase it, as you can see, as we increase the size, bending moment increases. Every time you increase the size of the link beam, the bending moment will increase. And the capacity may not be enough. You may keep increasing. Every time you increase, bending moment also increase. So you may end up with a situation that you cannot design this link beam because size cannot be. You increase the reinforcement, it may not still be enough. So sometimes we have to allow these beams to yield. That means we have to use capacity-based design we talked about last time. We have to allow these beams to have hinges, and that is very important. And in fact, that is the main purpose of these link beams, to be designed as hinges, to be designed as energy dissipation devices. So they become like our friends for this seismic design. And we rely on them to provide limited capacity between frame and shear wall. So I will talk more about the link beams as we go along, but this is very important part of the tall building. Coupling beams, we call them coupling beams or link beams, that connect the shear wall to frame or connect two shear walls together. And that is the axial force in the column. Now this is very interesting. You can see from here that when you apply the lateral force, this column has almost very small axial force, but this column has a large axial force here, compression here. In this case, when we increase the size of the beam, this column starts to have larger axial force. That means more shear is being transferred from this to this column. And when you increase that, this column has a very large axial force. So which means now this column is acting to balance the deflection of the shear wall. It is propping the shear wall. The point is that depending on the bending capability of the link beam, you can control the deformation of the shear wall. So the shear wall deflection, lateral deflection can be controlled by a column by the link beam. So if the link beam is weak, the shear wall will bend, and the link beam will also bend, and column will not support. But if the link beam is strong, then the more force will go to. So you feel the force on the column. That's exactly. So we use the axial capacity of the column to reduce the lateral deflection of the building. That is a very, very good thing to do, because any time if you can resist a force by axial is stronger than bending. Truss is stronger than beam in most cases because all forces are resisted by tension and compression, axial members. So if the building behavior can also be such that the lateral forces can be resisted by axial forces, then you will have a stronger building, more efficient building, rather than bending and shear. So that is the purpose of the link beam, that we provide the link beam, strong link beams, to transfer the load to the column by axial force, right? And the link beam strength can be controlled to provide just enough, not too much. So we can provide the reinforcement in such a way that after a certain bending moment, it will yield. So it's a controlled device. It doesn't have infinite stiffness, it has yielding. So after some time, it will become, for some load, it will continue to be stiff, but after some load, it will yield and bend. So we do not, so I don't want to break my arm, right? So if the force is too high, I will let it go. But until I can resist it, I will resist it. So without breaking the arm, we use the arm to transfer the force between shear wall and the nearest column, and that is called the coupling effect. And that is where the shear wall and frame act together and increase the strength a lot, because the axial stiffness or axial reaction in the column is added to the lateral deflection, which otherwise is not present. Understand? So that is the key that you must remember. Whenever you can convert the bending action and resist by axial forces, that is the best way. And we are always trying to find a way to do that in tall buildings. Tube is the same thing. Tube converts the bending into axial stresses in the wall. And that is the shear that I was talking about. So you can see here, that is the shear between this one, shear is increased, and now the shear has become really large in the coupling beam. So we do not want the coupling beam to fail in shear. So this is where the capacity design comes into play, very, very important, right? So that is the whole, and you can see from here the reaction for forces from here. This one is like 53 something, this is 20, this is 7. So the reaction on the column is only 7 tons here, and it's 30 here, and it's 57 here. So you can see that this is providing a lot of support, so it's keeping the wall straight. It's not allowing the wall to bend. And that is being prevented through that link beam. So, like I mentioned, link beam, this coupling beam or link beam is the most important component in a tall building design, both in terms of controlling the drift, controlling the deformation, controlling the earthquake forces, ductility. I think this is one of the keys that you need to understand how it works. And you can do a lot of good design by controlling the link beams, where to place them, what is the capacity, how to design them. So they are a good tool to use in the design. We will talk more about this one. So shear wrecking problem. So last time I showed this slide also, that when something deforms, the frame deformed like this, and we have this delta, and this is a mode of deformation in shear. This is a mode of deformation in frame or bending. So flexural deformation and shear deformation, they come together in a building. So imagine this is floor number 1 or floor number 30, floor number 31, floor number 30, floor number 31. most important quantity that we are always looking for in a tall building is what? Drift ratio, right? Where did you learn that? Dr. Panchit class. Okay, so drift ratio is what we are worried about all the time, right? And that is what this is. This is the lateral displacement between one floor to the other, shear deformation divided by the height. So this drift ratio or this drift is what we are always worried about. How to control it. So two ways to control it. One is through frame and second is through shear or shear walls. So if you have a shear wall, then it will try to limit the drift in a story. If you don't have a shear wall, the drift can be large. So how much is the drift ratio limit? 1 by 1000? Yeah, 0.2%, 0.1% depends on a lot of things. So it can raise vary as that much. So that's what we are talking about, shear raking components. And then we have a story mechanism. So we are trying to prevent this from happening. We do not want any one story to just have all the drift or hinges, so it will fall down. Because if hinges develop in the columns, in any one floor on both ends, that's the end of the story. I mean, really end of the story. The building will fall down, no more story, and building will collapse. Lot of buildings collapse in earthquake is because of this thing. This hinges forming in columns and stories just falling down on each other completely. So this is the most important or critical thing that we don't want to happen. So we want to make sure that this does not happen, and we always prevent or check for this one. That's why shear wall is very important, that it does not allow this to happen. Now we come to the question that I want to show you, coupled walls. Just now we saw coupling between frame and wall. So one side is frame, one side is wall. Now we are talking about another coupling, even more important than the frame coupling. Two walls side by side connected by a coupling beam or a link. Why this is important? Because most of the time, this is one scenario. What is this? Elevator wall, right? You need a door to enter. So one side of the wall will be punctured by a door. So which means that now this side of the wall and this side of the wall are only connected by this link beam because of this opening, and this creates a weakness in the wall. And now this on that side, this is one wall. Here it becomes two walls connected by a coupler. It's not, so you can think about a wall with opening, or you can think about two walls connected by a beam, right? So now these two walls, how much strength can they provide? Can they provide the strength and stiffness equal to the wall behind, or are they going to provide stiffness equal to these two separately? You know that this stiffness will be like 1/10 of that stiffness, because each wall is separate, and stiffness is equal to BD cubed by 12. So that depth is very large, this is very small, so it will be very small. So which means that if we, like same thing here, if you have a wall here and you have openings, basically this wall now becomes ineffective, and we have two walls connected by link beams, and their stiffness much less than the original wall. Then we need to rely on coupling, wall coupling, or those coupling beams that I mentioned to you. So same thing happens as it happened between frame and shear wall. Two walls also interact with each other through the stiffness of these coupling beams. So let's see some examples. So now these coupled shear walls are controlled by these three parameters, a few parameters. So this is one wall, basically this is one wall with openings, so it basically becomes one wall and second wall connected by beams with the height of that one. So these parameters now determine how this wall will perform. And we are always in trouble in tall buildings because Architects obviously want openings in the walls. We don't, but they do. And we are always trying to look for two walls in the building, which may be very far, and trying to connect them somehow. Because if we can connect two walls together, the sum of the total stiffness is much more than the sum of the stiffness. So if this wall is stiffness 10, this wall is stiffness 10, total stiffness is not 20. It can be 30 or 100, depending upon how we connect them. So that is our main target in tall buildings, to look for two things. First is we look for a wall and a frame to connect them together by a coupling, and we look for walls and walls and try to connect them by a coupling, so that we can take advantage of this coupling effect between walls and take advantage of the coupling effect between frames and walls, because we know that the sum of those stiffness will be much larger than their original stiffness. Number one. Secondly, we can control the ductility through those link beams by putting hinges there. So like I mentioned, both stiffness and hinging, both properties that we desperately need in a tall building, can be provided by linking frames and walls or linking walls and walls. So these one become equivalent like this. So now when we model it, we model this as one wall, we model this as one wall, and we put beams representing this link. And this beam can be then a nonlinear and all of that stuff. So let's again try and see how this is not in your previous slides, I added them yesterday. So you can see. So now we can see the effect of the size of the coupling beam on the behavior. So we started with a small coupling beam, medium size, large one, very large one, and see how the two walls act together, right? So this is small, this is a small building, but the idea can be seen. So you can see from here, when we apply the force, deflection from here to here, that much deflection. And then these coupling beams are completely bending, and they're not providing much support. Each wall is almost bending independently, freely. So no coupling, very little coupling. So 1 plus 1 is 2 in that case. When we increase the size a little bit, the deflection reduces from here to here, and the deformation pattern change. When we increase further, deflection further reduced from there to there, and when I increase it substantially, deflection only becomes like this one. So you can see from here the deflection here was that much, and here it's only that much, 1/10 or 1/6 of that deflection. Same walls, just changing the coupling beam size has reduced the deflection by 5 times. That means increase the stiffness by 5-6 times. So 1 plus 1, no longer 2, is 5, because of the coupling beam that we add. And these coupling beams then can of course be designed. Obviously you cannot have very big coupling beams, but I'm just giving you an example how you can control the behavior of a tall building by the size and stiffness of the coupling beam. Sometimes if the size cannot be increased, we replace them by steel beams, so high stiffness. So many things can be done, but important thing is coupling needs to be increased to reduce. So we can add just enough coupling to get the right drift. Let's say the drift ratio or the deflection we are looking for is 15 centimeter. Here maybe it's 40. Here it is 30, 20, 5. This is too much. We don't want it. So we can stop where we need it. So we can optimize the performance of a tall building by optimizing the size of the link beam. So we can look for the right size of the link beam that will provide just enough stiffness that we require. Not too much, not too less. And we can also provide hinging to make sure that when it's strong earthquake, it just has hinging and does not cause failure. Sometimes we design these coupling beams to be replaced. So they can actually be steel beams, they can be replaced if they are damaged. Bending moment in the coupling beam, you can see here, very small, medium, very large. And here I did not model it as a beam, I modeled it as a shell, so I could not see the bending moment, but it will be much larger than that one. So you can model the coupling beams as shell, or you can model it as a beam. But you can see how this thickness of the coupling beam keeps increasing the bending moment in those. So you have to make sure that you design these in such a way that they never fail in shear. They fail in moment first. So shear capacity must always be larger than the bending capacity of these coupling beams, because we never want them to fail in shear. Otherwise it will break and then everything will go, then the building will fall down. So we must have controlled failure, which is by putting flexural hinges there. It's not so clear on your screen, but you can see the stress is also different. Here, if you can see a little bit, tension, compression, tension, compression. So which means each wall is bending as if it was an independent cantilever. Each wall has tension and compression on each side. Here, little bit less. Here it is disappearing. Here, tension, compression. So the two are acting together now. So that is the shear. So that's the advantage of using line element, that you can get all these forces easily. Difficult to get them for area element unless you put section cuts. So you can see shear increase quite a bit. And if the shear capacity is less than that, we don't want it. So we have to limit it based on the shear capacity. And you can also see the reactions here, that here the reactions of these vertical forces change quite a bit. Here it is 130 something, and here it is 290. The total sum of these forces, and that will be different in each case. So you can see that the size of the coupling beam affects everything. It affects the drift, it affects the bending, it affects the shear, and it affects how the two walls or frame work together or don't work together. So we can use this to decide whether we want two walls to work together or not, and how much, by controlling the bending moment capacity, because that can control shear capacity. But that is only possible for earthquake. For wind, we do not have that option. So in that case, we must design it based on the capacity of the link beam. So this is an important consideration in tall buildings that bothers the engineers all the time, like he was mentioning. Second is now core coupled structures. So that is between one wall and one wall. But what about a core wall and the rest of the building? Can we connect them together somehow? Whole core wall system and the whole frame system, can we connect them together? Not one column and one shear wall like we saw just now, but can we connect the whole core wall or core of a building to the whole framing system? What are the mechanisms available for that? That's what we are going to discuss. So we are talking about this core wall and trying to connect it to all the columns, and this core wall trying to connect it to the outer columns. Same is the case here. So these are various options where you have a core, shear walls, and there are columns around that, but not directly connected to them like a frame, right? So the walls are not part of the frame. How do we manage that? So these are all core supported structures. These are all core supported structures. So these are cores here, columns are here. So there is no beam here normally running. So you cannot provide the link beams or coupling beams between the frame and the core wall. And that becomes a challenge. when you cannot do that. So you have the core walls, you have the frame, but you are unable to connect them through through coupling beams because these are very far and there is no way to do that. And the cores are very large and they are different in shape, so you cannot utilize the effect that we just saw just now. So all of these have the same issue. So what we do sometimes is that sometimes we have these core walls. Some of the frames can be selected where possible, some of the frames, but still most of the columns are not connected to the core wall. Right? So many options people have been trying, but they are not so effective in terms of the overall connection. But these are just some options. So sometimes the beams can be, and we come to this idea of outriggers. How many people know this term, outrigger? Yeah, of course you do. Anyone else? Okay, so that is the next tool we have as engineers for tall buildings. Very, very important component or tool for designing tall building is outrigger. Because outrigger allows us to connect the core walls to the outer columns without using coupling beams. So outrigger, what does the term mean, outrigger? What is out?
Outside.
Go outside, please go outside. So basically we're saying that we will go out from the core wall and try to rig something to activate the forces. So it's a rig. Rig means it's like a trick to use the outside columns with the core wall. So we call them outriggers. So these outriggers, core wall and columns which are very far, but beams are not present, can be connected through outriggers. This is one form of outrigger. There are many ways. This is one. We used it in some buildings. In fact, we used it in Manila, the tallest building there. That is the core wall. So this is the columns. So every floor we find one wall, one panel, and make it concrete. So it starts to act like a truss, right? So this one and this one acts like a truss, and that this becomes very strong, like a coupling beam, but a very big one, like a cantilever. So if that is a column over there, if I call him, no, he will not come now, somebody else. So we can use not one arm, but we can use these two arms together as a big cantilever truss and then rest it on the columns. Do you see this? So this is like a virtual truss, and this one also. So these are truss members, but they're not in the plane. But you create these virtual trusses from using parts of the walls, and then you activate the columns, because when this wall bends, these will make sure that these columns are activated in terms of their axial forces, right? So this is one way to do that, but we will do many others. Okay, where's the real core wall coming up? So we'll come back to the outriggers in a minute. So this is spinal systems, another system where we use spines, again outriggers and spines. So spine is like human spine, so we have this main spine, around that the building is constructed. So we have spine, and this is all made from, the spine is made from outriggers and walls together, and then you build the building around the spine and then tubes. Okay, coming back to the outriggers. So outrigger and belt, two things work together. Normally they are used as a set. Outrigger and belt. What's a belt? Right? This one is belt. What is it doing? Holding my pants up? No, belt is basically connecting the outside thing together, right? So we will use the belt and the outriggers as a group to solve the problem of connecting the core to the frames. So this is now the outrigger and core basic concept. Same as the coupling, but not used on every floor, only used on some locations but very deep. So basically from the core wall we create a big cantilever or a big beam and then connect it to the column. So same thing that we did earlier, but now it is longer, very far, but very deep, right? As deep as 2 floors, 6 meters, or 3 floors, 9 meters. Big beams, very huge beams, running two or 3 floors together. So these very big beams connect the outermost column, we call them super column, and connect the super column and the core wall, and they are placed in few locations. And then at the outside, we sometimes use the belt. I will show you the belt also. So the idea is the same as the coupling beams, but instead of using many, we just use only 1 or 2 or 3 in the whole building. And they exactly do the same thing as the coupling beam. So outrigger and belt system, I will show you the belt also. So let's see outriggers. We have done a lot of research on outriggers. Every year, 1 or 2 students do some research on outriggers, some kind of research. This year also a few people are working on it, because we are still trying to figure out what is the best location of an outrigger. How many outriggers should be provided? What should be the size of the outrigger in a tall building? Should it be just 1 outrigger? If 1 outrigger, which floor it's most effective? First floor, third floor, 10th floor, 20th floor, top? How do you decide where to place the outrigger? How do you decide how many outriggers are needed? How do you decide what is the best size of the outrigger and number of the outriggers? So this is a question still unanswered, kind of, because it depends on many things. So this is just a quick study of the outrigger. This is building without outrigger. Here I put the outrigger at the top. Sometimes we call it hat. If you put it outrigger at the top, we call it hat, right? So if I put an exam hat, don't confuse it with a normal hat. We're talking about this hat. So outrigger in the middle, hat, and let's see the effect. So that is the effect of the outrigger. So this is the displacement without outrigger. This is after we add 1 outrigger at the top. This is the displacement when we add 1 outrigger in the middle. What do you see here? What do you see? Which one is the best one? Yeah, why?
It's created the kind of
No, first of all, how did you decide it's the best one?
less displacement.
Less displacement, exactly. This has the least displacement. So it means that the one hat is not the best idea. It needs to be somewhere in the middle. And after that, because we control it, we need to control the shortening and anything and deformation of the wall as much as, because on the top it's not so much. So this location is very critical. Where is the best one, right? This is only 8 stories. If you have 70-story building, where do you place it, right? It's an interesting topic on how to find which is the best location, right? Anyway, so you can see that when you put the outrigger, the displacement reduces a lot and many things become much better. Of course, architect will not allow you to place it anywhere, so you're not actually free to do that. The problem is that even if you find the best location, the architect may not let you do that because that floor may be a very high-end floor where they won't allow you to put these walls. So you have to compromise. You have to work with the architect. Which floors are available? Normally, we are looking for floors which have services. Normally, they put the generators and AC power plants or something like that on somewhere in the middle of the building. And you are looking for that floor. And then we try to put the outriggers on the services floor. Or we talk to the architect and, sort of, but the problem is some buildings don't have service floors, like residential buildings. do not have service floors. So then you cannot find an outrigger location. Very difficult. So even though we know structurally which is the best location, you cannot actually use it because of the architectural constraints. So please look at this one, the effect of the outrigger on the axial force. So here the axial force is gradually becoming large because each beam is adding some shear. So we have the total force coming up here. Here you put the outrigger. So mostly the axial force is added all the way. Not very efficient because all the columns have to be now designed for large axial force. Have to be made bigger. Here the axial force starts in the middle. These columns do not need to be designed for axial load anymore. So this is very efficient because it needs least amount of column, super column or reinforcement, right? And the columns above are normal. So below that you need special column and there's a lot of force. And here the effect is also more. This is more efficient because it's transferring more axial force to the column. That's why the drift is small, right? Because more axial force was able to transfer in the middle. So it is sure that outrigger somewhere in the middle will be more effective than the one at the top. But sometimes we have no option. Roof is possible. Sometimes a hat is possible because nobody is living probably at the roof, so you can put a beam there. Although now many people have roof gardens and roof terraces and roof restaurants, so that is also not possible. But many times it may be possible to put this one. But this is more efficient, more structurally, it's much more beneficial. Wall stresses, you can see that wall stresses, so this is the stress diagram within the walls. So this is the pure tension compression. Here there's a bending, so tension compression changes near the outriggers. Here's a complicated stress flow. So when you put the outrigger, the stresses in the wall become quite complicated in that area. So reinforcement layout, reinforcement detailing between the core wall and the outrigger becomes a challenge because the wall is now going into reverse bending at that location. So it's not just a free cantilever anymore. So many things have to be studied for outriggers. Bending moment, also you can see here that outrigger greatly reduces the bending moment in the beams. Look at this one. When you put the outrigger here, the bending moment in all the beams and columns was reduced. And this is the advantage. You can reduce the reinforcement in the beams substantially by putting one outrigger. So instead of putting many beams and putting a lot of reinforcement everywhere, we just put one big outrigger and reduced all the beams reinforcement. This is very, very useful when you have very tall building because you can reduce reinforcement in 30 stories by adding one outrigger, right? So there are many benefits to providing outriggers if we can manage it. But many times we cannot. So what do we do? TMD. No. TMD. Forget about that TMD. That will not help us. Not now. What do we do if we cannot solve a problem? If we cannot get what we want, what do we do? Let me put it this way. Compromise. Always think about compromise. If you cannot get what you want, try to get as much as you want, not all. So we talk to the architect and we say, okay, I want an outrigger here, but I will let you have some openings for your doors. Let's talk about this. Then you work with the architect and give punctures or holes into your outrigger. It reduces the efficiency a little bit, but you still get most of the benefits. So you try to use the outriggers and talk to the architects or talk to the owners and say, okay, I will let you have your opening, or can you move the opening here, something like that. So many times we are able to provide outriggers with openings, and again we did some research on that. research beam master's thesis on this one, outriggers with openings. How do they perform? So how do they compare to the outriggers without openings, right? Because then you can place them in many locations. That is the shear, and again you can see the shear force in all the beams is reduced. Such a beautiful solution to a tall building, because when you put an outrigger, then the bending moment in all the beams is reduced, shear force in all the beam is reduced, the displacement is reduced, everything works beautifully. So tall buildings are primarily designed with shear walls, frames, outriggers. So a real tall building will almost always have some outriggers, some shear walls, some frames working together, right? And it is the combination of these that you can play with to optimize the building performance. So, two-story deep, sometimes we do this one, wear and deal. How many people know the term wear and deal? Of course you know. Who else? Wear and deal. Where's the girl who knows hyperbolic paraboloid? Where's she? Ah, okay. Another term to remember and impress people, wear and deal truss or wear and deal girder. Okay? So wear and deal girder is a girder which is made from frame. The best example of wear and deal, how many people have gone to Asok, BTS, Asok Junction? Okay, few people. There's a bridge over the Asok. If you come from the Asok road and the Sukhumvit, the bridge on the Sukhumvit road under the BTS, there is a bridge. That is a wear and deal truss because it is made from vertical columns and horizontal beams by a moment connection, but it's a truss. So you can sometimes create beams like a truss with openings called wear and deal truss, and that is exactly what you can do, as I mentioned to you, and give these openings to the architect, right? Compromise. So the outrigger doesn't have to be a solid beam. It could be a wall with one or two openings, or it could be a specially designed 2-story or 3-story ductile wear and deal frame, including, who asked, hinges just now? Yeah. So now you can put hinges also here. So there are again innovation, people thinking about the problem, finding the solutions, and solving the problem. So many things can be done. So you should just have to focus, what is the problem? What can I do to solve this problem? And then you will see that you can find many solutions. So this is one solution. 2 or 3-story wear and deal trusses or girders acting as outriggers, designed specially for that purpose, including ductility or hinges. So cap wall system, as I told you, cap. So sometimes we can have cap, and we can put these two as caps on, and then these columns can take it. So caps also possible, but caps not so efficient as an outrigger in the middle. So this is just, somebody did this study, not our, we have done in concrete, but this is some study coming from someone. One outrigger, they compared how much deflection is reduced, outrigger moved down, outrigger moved down. So different location of outrigger, you can study the effect on the frame displacements and column shears and everything. So you can see outriggers reduce the bending moment in the wall, core wall also. If you go back here. So you can reduce the bending moment from the core wall. Question: can the outrigger reduce the shear in the shear wall? Does the outrigger reduce the shear in the shear wall? It's an exam question. Give me opinion. What do you think? He's saying no. No. Exactly no. It cannot. Because outrigger cannot, because it's axial force in the column. So this has no shear, no horizontal component. So outrigger cannot reduce the shear force in the shear wall. That is a limitation, or that is, so shear wall still needs to be carried by the column shear and the core wall or the walls. So that does not help. So there is always a limitation that if you have a problem in the shear wall shear, you cannot solve it by outriggers. Some people misunderstand or think that they can reduce the shear force in the core by adding outriggers. It won't work. It doesn't affect it. So you can reduce the bending moment in the core wall, you can reduce the drift, you can reduce the displacement, you can reduce the initial period, but you cannot reduce the shear force. Okay? Even though it's the exam question, I'm still going to ask it and see what you do. So optimum location of a single outrigger. People have done this study and they have come up with this idea that okay, this portion will be the best one. And then this is a belt wall. I will talk about the belt wall in a minute. So you can find an optimum single location by studying all the locations, and you can say, okay, this is the best location for an outrigger. It's about this region. And then optimum location, people have studied many things. So recommended optimum locations for multiple outriggers. So a lot of research has been done on outrigger number, location, and effectiveness. So 1 outrigger, 2 outriggers, 3 outriggers, 4 outriggers, according to the height. That's roughly where it will be, but it changes a lot on the actual building, so it's not fixed for every building. It depends on many things: frame, column, number of size of shear wall, many things. Okay, sorry, I forgot about the belt. Why I forgot about the belt? Why belt is needed? Let me go back to this one here. So the problem is that if you have one outrigger here and it is resting on one column, then that one column has to be made very big. But architects do not allow or want some columns to be bigger than others for many reasons. So what we do is that we, on this side, also we provide a big beam that will distribute that load to many columns. So that becomes the belt. So in that floor where the outrigger is provided, we also connect all the columns by a beam which acts like a belt. So the load from the outrigger is distributed to all the columns. Do you understand? Okay, good. So belt and outrigger often go together. Sometimes the architects will not allow you to provide belt because they have windows. They don't want you to block the windows. In that case, you have to design some columns to take the force. Those columns can be composite, steel columns, high strength concrete. Many things can be done. So normally you need to have these called super columns or a belt system to distribute the load to many columns. So frame and shear wall, we have already talked about it. Now we come to the last main system. I need to finish this topic today. Main system, tubes. We talked about tubular system. The beginning, I mentioned to you that this is one of the main innovations in structural engineering for tall buildings, that outer tube, I used your bottle last time to show how the whole section of the building can be used to resist the lateral forces. So that means you basically provide closely spaced columns and small and beams, and you make the tube on the outside. So the whole building acts like a tube. It's like a building is conceived of a big shear wall with openings. That's what we think about the building. That it's a big shear wall with openings for windows, so columns and beams become part of that tube. So this is the most common, most famous example of the tube system is the two towers that were destroyed on 9/11. They were the first ones to be made from tubular system, and they also had a weakness which those people knew somehow and exploited. So some structural engineer must have looked at the weakness in those tubular systems, because if it was designed now, that wouldn't happen. Because that tubular system was designed in such a way that the core and tube were not connected at all. Outer tube was independent steel columns and nothing in between, and the floor was simply resting on the core and the outer wall. No interaction between them. The floor was very thin and it was not rigidly connected, and there was just pin connected. Core and outer tube was just pin connected. So when one floor collapsed, everything went down. But now after that, you normally need to connect the tube with the outer with strong, we call them arrestor floors. New term has come up, arrestor floors, so that this thing will not happen again. So if you can see a little bit, that is the tube. Can you see it? Okay, so this is the tube, solid tube without any openings. And if you put some openings in it, it will be openings until you make the opening larger, then it becomes a frame. So you have to think in a continuous transition from a wall to a frame. So this is a wall with no openings, this is a wall with small openings, this is a wall with large openings, this is a wall with very large opening, this is a wall with very, very large opening, become a frame. So when it becomes frame, when it's a wall, actually anybody's idea. I can say this is for this one, I can say this is a wall with large openings. Or I can say this is a frame with big columns and big beams. Both terms are correct, right? Correct? I can say these are very big columns and very big beams, or I can say it's a wall with openings. Tube is exactly doing that. Tube is thinking about the whole building as a wall with openings, and then you design it in that way. So you don't design it as a frame. You don't think, and you keep the columns closely spaced and the beams deep enough. So instead of having so typically the tubes remain in this range rather than going to that pure frame. So tubes remain in this range. So they are still considered to be walls with openings, and that's why they can be designed as in a different way and can be designed to carry the forces. So if it's a full solid wall, same loading, displacement is 0.17. If it's a very, very thin frame, displacement is very large. But if you consider it in the middle, displacement is actually not that big yet. Right? Between solid wall and wall with opening, the displacement is not much different, not compared like this one. So after some time, it starts to become very large. So we remain in this range in the tube, so that the wall effect is still present, and the stiffness of that system is not much less than the pure solid wall. So we consider the whole building outside surface as a wall with openings. So that's how understanding shear lag. Now the problem is, this is the wall, building core, but not core, the whole building, and then we are thinking about it as a wall with frames. So when the If it is a solid one, then it is governed by the shear stiffness. When it is frame with closely spaced columns and beams, then you have some frame effect coming into that, this I showed you. And that is called shear lag. That means the leakage of the shear stiffness because of the frame action inside the wall. If there is no frame action, only wall, you will not have shear lag. But if you have openings, each opening creates a small leakage of the shear because of some axial deformation. So that shear lag or loss of the shear is what we are worried about. So if the shear lag becomes very large, then it becomes a frame, and then we cannot use it as a tube. So we must control the shear lag to be within a certain range to be effective as a tube. Shear lag is the deformation because of the deformation of the small columns and small beams, bending of those, right? So main concern in a tube is shear lag, and we need to minimize the shear lag. So you can see from here that pure wall, if you think about this as a cross section, tube cross section, if you apply the forces, the ideal situation should be linear strain distribution, but it will not be linear. It will be a little bit non-linear because of the shear lag. Because if the cross section, you remember in the first course we talked about linear strain distribution for a column or a beam or a tube. But if the strain distribution is not linear, that means we have a shear lag which is causing it to be non-linear. So in a tube system, it is non-linear, not linear. And that is non-linear because of the shear lag. And we always try to minimize that shear lag. So you can see the difference between, so this is the idealized stress distribution, linear stress distribution, tension here, compression here, and linear variation on this side. But for a shear lag, it will go like that. So it will be more concentrated around the corners, less concentrated in the middle. So linear, non-linear distribution of stress is caused due to the shear lag phenomena for the tubes, which is coming from the local deformation of columns and beams, right? Tube can be free-form. Any configuration can be tube. So it doesn't have to be just like a cross-section. You remember cross-section builder? You can create any cross-section shape and it can still analyze it as a cross-section. Same thing here. You can create the building in any shape, it still becomes a cross-section of the tube. So it's a tube with a different cross-section, just like that. So you can think like that. So any possible, that's why the architects are now taking advantage of this idea and creating all these buildings of all kind of forms of donuts and whatever not, because they know that engineers have found the secret to design it as a tube, tubular section. So whatever shape they create of the building, we can conceive it as a cross section of a tube and design it accordingly. So irregular tubes, you can see here. The problem with irregular tube is that the stress variation will be like that, abrupt changes. That's something that you have to, compression will not be smooth, nonlinear, highly nonlinear distribution of forces around the tube. So that means column forces and shear forces in the frame components will be very irregular. You need to be aware of that. As long as you can design it, it's fine. And sometimes, I mentioned to you last time, to reduce the shear lag, you can put diagonals, bracing into the building to reduce that effect of the shear lag. So you can put big diagonals and that will act as a truss. So this will be a complicated system having a tubular behavior, of local frame behavior and a global truss behavior. So you can see engineers are very innovative, have been innovative. Your seniors, they have always come up with very good solutions whenever they face a challenge. That's the building with diagonal exterior tube on Trade Center in Chicago. Famous building because it's tube and braced, beautifully done. Then last item, 2 minutes now. Bundle tubes. Sometimes one tube is not enough. For very tall buildings, one tube is not enough. You need to create many tubes together, just like you take many straws and put them together, bundle them, and it becomes strong. Same thing, you take many small tubes and put them together, and it becomes a good system. So this bundle tube concept also originated. And they said, why, if one tube can work, why can't we put many tubes together? So here 3 tubes are put together to form the system. Rather than doing just one tube outside, they say, oh, let me one tube, second tube, and weld them together. Like, so you take 3 tubes and you put them together and weld them. Imagine like that. So this multi-tube concept came up. So you can see here multi-tube, bundle tubes. And then bundled braced tubes came up. Keep on going, never ending. Just keep on adding ideas, putting them together, trying them. Real buildings with bundle tubes, various configurations. Most of the tall buildings, very tall, like the Burj Khalifa in Dubai is 15 bundle tubes. It's a combination of 15 tubes put together. You don't see them, but if you carefully study, you can actually isolate them of various heights. And then some miscellaneous systems we talked about. Steel structure I'm not going to worry about. Selection of structural system, okay, we cannot discuss. Let's stop now here.